Okay, uh, in the last lecture, in the class, we discuss diamagnetic material. Okay, and we already discussed there that diamagnetic materials are those materials whose outermost shell contain only two electrons. If there are only two electrons, then one electron has a spin 1 over 2 and another has a spin minus 1 over 2. So one electron move clockwise and another electron will move anti-clockwise. The clockwise electron will produce a diamagnetic moment mu m whose direction is upward, and the anti-clockwise electron produce magnetic moment whose direction is downward. If we calculate the net magnetic moment, which will be magnetic moment of the electron whose with spin 1 over 2 and minus magnetic moment of electron with spin minus 1 over 2. This is by vector addition. Okay, the minus comes from the direction because its direction is downward, its direction is upward. The upward direction is taken to be positive and the downward direction is taken to be negative. So as a result we have a net magnetic moment which is equal to 0 in the absence of external field. If we apply external field, then there is a net dipole moment delta mu m which comes from the application of magnetic field. I am not going into the detail of diamagnetic material here. Now, paramagnetic materials are those materials which contain whose valence shell contain unpaired electron. That is, the valence shell electron either contain 1, 3, 5, 7 and so on. Are those material in which the valence shell contain only one electron. Now, suppose we have an atom with valence shell which contain only one electron. Now, this electron either has spin s is equal to 1 over 2 or its spin is minus 1 over 2. If its spin is 1 over 2, then the electron will move in clockwise direction. If the spin is minus 1 over 2, then the electron will move in anti-clockwise direction. Now we will consider the first case where the spin s is equal to 1 over 2. Suppose we have an atom in which there is only one electron in the valence shell and the electron has a spin 1 over 2. Then the situation will be this one. This is only one electron and it is moving in a clockwise direction. Now the current will be in the if it's moved in a circular path, so due to this movement there is a current and the direction of current will be clockwise. Now due to this current there is a magnetic field, and we can calculate the direction of magnetic field by the right hand rule. And in the present case we already discussed all this rule in the classroom. Okay, and the direction of magnetic field, so in this case the magnetic field originates from the top surface. So the top surface will be the north pole and the bottom surface will be the south pole. And we know that magnetic dipole moment direction is from south to north. So it's from bottom to top, like this one. Okay, so the direction of magnetic dipole moment is mu m. Now if we have atom in which the electron spin is -1/2, okay, S is equal to -1/2, then the electron will move in anti-clockwise direction and the current will be clockwise. This is the direction of current. Now here the top surface will be the south and the bottom surface will be the north, and we know that magnetic dipole moment is from south to north, so the direction will be downward. Now paramagnetic material contain many electrons, okay. There are many electrons, many atoms, sorry, in the material. Suppose we have the paramagnetic material, okay, and we have many atoms, so I am considering only a few of them. Now this atom's dipole moment is suppose is this one, and suppose this atom has a dipole moment like this. This atom might have a dipole moment in this way, and this atoms might have a dipole moment in this way, and this might have a dipole moment in this way, this might have a dipole moment in this way, and so on. So all the atoms have a dipole moment mu m, but they are randomly oriented. Now if they are randomly oriented, if we calculate the net dipole moment, then the net dipole moment is, suppose one atom has a dipole moment is this one, the other one has a dipole moment is this one, the other one has a dipole moment is this one, the other one has a dipole moment is this one, and so on, and finally and the last atom has a dipole moment is this one. Then there is no resultant dipole moment, because by vector addition we don't have the resultant vector, because the tail of first vector, the head of last vector coincide the tail of last vector. So as a result we have zero net dipole moment in the absence of magnetic field. Magnetic field is zero. Now if suppose this, we have a single atom whose dipole moment is this one, okay, so this is south pole and this is north pole, and suppose we apply the magnetic field in such a way, then this is I think this is north pole, and this will be north pole and this will be south. Now what's happened, this north pole and south pole will attract each other. Similarly, this south pole of the dipole moment attract the north pole of the external magnetic field. So as a result, this dipole moment rotates itself in such a way that in the external magnetic field it's ally itself in such a way that this is the south pole now and this is the north pole. So the dipole moment ally itself in the direction of magnetic field. Same is true in the case of material. If we apply the magnetic field here in this material, suppose we have this the magnetic field, and the atoms, they have randomly oriented magnetic field, now ally itself in the direction of magnetic field. So this atom with dipole moment rotate itself in this way, this one will rotate itself in this way, this one will rotate itself in this way, this will rotate itself in this way. So finally all the dipole moment of all the atom ally itself in the direction of magnetic field, and as a result we have the net dipole moment, which is not equal to 0 now. So in the presence of magnetic field we get a net dipole moment. Now if the magnetic field is weak, if B is weak, So if the field is very weak field, then only few atoms will ally itself in the direction of the magnetic field, while rest of the atom will not ally. For example, in this case, we have this atom which ally itself in the direction of magnetic field, because it's easy for the magnetic field to rotate this dipole moment. But this dipole moment, it's difficult for the magnetic field to ally the dipole moment in its own direction, because for this alignment we need a strong magnetic field. But as we increase the magnetic field, if B is very strong, then all the dipole moment ally itself in the direction of magnetic field, and we have the maximum magnetic dipole moment. And once we get the maximum dipole moment, then we attain a condition which is called saturation condition. Saturation condition means the magnetic field where all the dipole moment ally itself in the direction of magnetic field, then we have the maximum dipole moment, and we have a saturation condition achieved, where we get the maximum dipole moment. Now the alignment of dipole moment also depends on temperature. Suppose we have the room temperature, and at room temperature we apply a strong magnetic field and we get the maximum dipole moment. But as we increase the temperature above the room temperature, then what's happened? Each individual atoms now vibrate up and down, or left to right, or in any direction it will vibrate. Once it vibrates by increasing the temperature, then initially the atoms whose dipole moment direction was this one now might have a dipole moment direction becomes like this by increasing the temperature. So it means that there are two components of the dipole moment now. One is this, one is this one. Now this component is in the direction of magnetic field, which is very small as compared to this dipole moment, which was initially like this. Similarly, for the other atom, there is again vibration, and due to this vibration the dipole moment might be reduced to this one, okay, or might get a position like this one. So here again we have two components. So this component is in the direction of magnetic field, which is slightly bigger than this one but smaller than its original dipole moment when the temperature was at room temperature. So as a whole, the net dipole moment decreases, because initially we add this with this, we get a net dipole moment. But in this case we add this with this, so we get a net dipole moment which is smaller than this one. So it means that the dipole moment, the net dipole moment depends on temperature. By increasing the temperature, the net dipole moment of the material reduces or decreasing with temperature or increasing with decreasing temperature. This is all about paramagnetic material. In the next video we will move to the Langevin paramagnetic equation. Thank you.